In the last video, we looked at what the weak nuclear force does. In this video, we're going to look at how you can determine whether or not an interaction is possible based on the conservation rules. And the conservation rules are about quantum numbers. And quantum numbers make it easier to talk about things like charge. Imagine how complicated it would be when trying to work out the composition of a particle if we had to keep using 1.602 times 10 to the negative 19 coulombs as the elementary unit of charge. So instead, we use E. And we have charges in terms of 1e, or a third e, or minus a third e, and so on. It's similar with energy levels. Within atoms, electrons orbiting atoms can be at n equals 1 or n equals 2. And as you probably learned about in chemistry, there are also subshells for angular momentum quantum numbers. But there are some other quantum numbers as well. For example, baryon number, strangeness. Is there a lepton number? Well, yes, there is. And so these quantum numbers are what we are concerned with when we're looking at those conservation rules. So a reminder, baryons have a baryon number of 1, antibaryons have a baryon number of -1, mesons and leptons have a baryon number of 0. Charge, well, that's either taking -1/3 for a down quark, +2/3 for an up quark, -1 for an electron, +1 for a positron, and so on. Strangeness, if you remember, is following the charge of the kaon. So a K plus has a strangeness of +1. And K minus has a strangeness of -1. And that's because a strange quark has a strangeness of -1. Don't get caught out by that. Now, baryon number and charge are conserved in all interactions, but strangeness isn't, because the weak interaction can change quarks from one type to another. Remember, the weak interaction is the only one that can change a fundamental particle, an elementary particle. So strangeness is not always conserved. It is conserved in strong interactions, electromagnetic interactions. And I've listed here gravitational interactions, but we really don't know very much about gravitational interactions for particles. Gravity is just too weak. But we know that the strangeness is not conserved in weak interactions, because that's how quarks can decay. So what about lepton number? Well, lepton number is a tricky one. On the face of it, it looks straightforward because electrons, muons, electron neutrinos, muon neutrinos are all matter, not antimatter, so we can give them a lepton number of 1, and antimatter particles that are leptons, we can give a lepton number of -1. But there are different generations of those leptons, those families of leptons. The first generation of leptons, the lepton number is conserved separately to the second generation, which is conserved separately to the third generation. You don't have to worry about third generation in your A level, although it's no more complicated. But the first generations, the electron generation and the muon generation. So electron lepton number is conserved independently of the muon lepton number. And these lepton numbers are always conserved. Now, that's not quite true, in fact, and it gets more complicated when you look at what happens to leptons as they travel over very long distances. Neutrinos, in particular, can change from one type to another when they move over very long distances. There are also things called sterile neutrinos, and the world of particle physics is much more open and exciting than we can cover in this series. But let's just stick with our first two generations of leptons and the idea that in an interaction, the lepton number for electrons and the lepton number for muons are conserved. So this is the table of all of the quantum numbers we are concerned with in A-level physics and all of the leptons down that left-hand column. You'll see the last two columns, baryon number and strangeness, are fairly trivial for leptons because leptons cannot contain quarks. They are fundamental, so they can't contain quarks. They can't possibly contain strange quarks or strange antiquarks. Leptons can't contain any quarks at all, so their baryon number is going to be 0. So all we have is electron lepton number and muon lepton number. Oh, and charge, of course. So a better way of writing our conservation rules is like this. Baryon number, charge, electron lepton number and muon lepton number are always conserved. Strangeness is only conserved in the strong and the electromagnetic interaction. I have included gravitational interactions here, but again, we don't really understand how that works. So we might be interested in whether certain decays are possible or not. So here's a muon decaying into an electron. It also decays into an electron antineutrino and a muon neutrino. And perhaps we're interested in whether or not this decay is possible. So what we do is we list our quantum numbers down the side here. Charge is conserved. Electron lepton number is conserved. Muon lepton number is conserved. Baryon number is conserved. Strangeness is conserved. So this interaction is possible. But here there's been a mistake. So we've got a muon decaying into an electron, but now it also decays into a muon antineutrino and an electron neutrino. In this case, that's not possible. And it's not possible because the electron lepton number is not conserved. It's 2 on the right-hand side, but 0 on the left-hand side. And muon lepton number is not conserved because +1 is not equal to -1. So this interaction isn't possible. And here's an example of a sigma plus baryon decaying into a proton and a pi0. Now, is it possible? Well, we've lost strangeness. The sigma plus has a strangeness of -1 because it contains one strange quark. And there's no strange quarks on the right-hand side. So strangeness is not conserved. Everything else is conserved, though. So this is possible, but only via the weak interaction. And pions can decay into electrons, positrons, and photons. And if you check the numbers, it all checks out. These are possible interactions. But just because an interaction is possible in terms of quantum numbers doesn't mean it's going to happen. These decays are trying to reduce the energy of the particles. Whether that's the energy of a nucleus, the energy of an atom, or even on the smaller scale, the energy of a baryon. They're trying to reduce that energy. If you look at this chart on the right, the numbers we're concerned with correspond to strange quarks, up quarks and down quarks. And you can see a strange quark can decay down into an up quark, and a down quark can decay down into an up quark. And that's because the up quark is slightly less massive than a down quark. It is possible to go the other way if it reduces the energy of your composite particle. But if, for a fundamental particle, we're looking at decays all by themselves, then you're going to cascade down in energy, emitting energy, and thus reducing the energy of your particle and increasing the entropy of the universe. In this diagram, we haven't included Z0 bosons, which would cause a strange quark to decay down into a down quark. You can see that for a strange quark to decay into an up quark, it has to move to the right. It has to increase the charge by 1. So therefore there's an emission of a W- boson, so that the particle increases its charge by 1. It loses negative charge, it gains positive charge. Now this means that up quarks can't decay into strange quarks, even by the weak interaction, even if the quantum numbers suggest it's possible. Just doesn't happen. So here's an example, a proton decaying into a sigma 0, which has a strangeness of -1, into a positron as well, and into an electron neutrino. And all the quantum numbers check out. It looks like it should be possible. But the sigma 0 is far more massive than the proton. So this decay wouldn't happen. Now, I suppose if you had a proton with sufficiently high kinetic energy, maybe this might happen. It's not observed, of course. So let's just say it doesn't happen. So that begs the question then, where do the sigma 0 baryons come from? Where do these more energetic particles come from if you can't use the weak nuclear force to decay a quark into one of the quarks necessary to have these more exotic particles? Well, the answer to that lies in the strong nuclear force, and that's what we're going to look at in the next video.